Hello and welcome to our new lecture where we are going to start with a new topic, which is the geostatic stresses or the stresses in soil. So talking about the soil stresses, the first question that comes to our mind is that what causes stresses within the soil? So for example, let's assume a uniform soil layer as shown here in the figure. Let's consider a small soil element as shown here. Now, what do you think if I ask you that what are the factors that are causing the stress on this small soil element which is present here? What could be the possible causes, in your opinion, that would cause stress on the soil element? Now, basically, there are two principal factors that affect or that cause stresses within the soil. One is the self weight of the soil. And what I mean by self weight is that on this small soil element present here, there would be a stress caused by the soil which is present above this soil element. So this soil layer which is present above this soil element would be causing certain stress on the soil element as shown by this sigma V. And similarly, some component of this vertical stress will be converted into the horizontal stress, sigma h. So the first factor which causes stress in the soil is the self weight of the soil above our point of interest. And the second factor which causes stress on a certain soil mass is the external loads. So any kind of external loads that we put on the soil, for example, we construct something on top of the soil, these external loads also causes stress on the soil. So in this coursework, we are going to discuss only the first factor, that is the stresses caused on the soil because of their self-weight. The second point is something that we'll cover in the next course of geotechnical engineering. Now, the question would be that how to determine the stress caused because of the self-weight of the soil. So how can I determine this stress which is being caused by the soil which is present above our point of interest? Now, this stress can simply be determined as the weight of the soil which is above our point of interest. And how can we determine this? The unit weight of the soil, there are in fact different cases that we can discuss. For example, we can say we can take the first case in which there is a uniform soil, and this uniform soil is such that its unit weight, which we generally consider as gamma, is constant. Now, if the unit weight is constant, how can we determine the weight of the soil above our point of interest? The weight of the soil or the stress caused by the soil above our point of interest can simply be determined by multiplying the unit weight times the depth of the soil layer. So if I want to determine this vertical stress acting on the soil mass at a certain depth, all I need to do is to multiply the unit weight with the depth of the soil element. So this is true only if if the unit weight of the soil is constant. But in reality, we often come across cases where the unit weight of the soil is not constant. Rather, in reality, what happens is that the unit weight of the soil generally increases as we go down in a certain depth. Why does it increase? Because as we get more and more layers of soil on the top, the lower layers get more compressed because of the weight of the soils on top of it. And this causes a further increase in the density or the unit weight of the underlying layers. So because of this, the unit weight generally is not constant, rather it increases over a certain depth. So if the unit weight of the soil increases continuously with depth, what we can do is we can again use the same formula that we had seen earlier, but since the unit weight is changing over depth, so we can simply integrate it over the required depth. And in certain cases, if we have a stratified layer, if we have a stratified soil stratum, for example, there are different layers of soil at the top and at the bottom. All we can do is we can simply take summation of the unit weight times the depth of each layer. Now, just while I'm trying to explain you simply the formula, it might look a little complicated, but let's solve a few example problems. And by solving those example problems, I hope these concepts and the use of these formulae would become more clear to you. So this is our first problem, and which says that the water table in a deposit of uniform sand is located at 1 meter depth below the ground surface. The basic properties of the sand are given, which is the specific gravity and the voids ratio is given to us. Now, we need to determine the effective stress at a depth of 6 meters below the ground surface under two conditions. Condition number one, given in blue underlined, is when the soil above the water table is considered dry. And second, when the soil above the water table is saturated by the capillary action. Now, how to solve this? Let's try to formulate the geometry of the problem first. So let's try to formulate the geometry, and it says that it is a uniform sand layer, and this uniform sand layer has these properties which are given to us. The specific gravity is 2.7, the voids ratio is 0.8, and the water table is located 1 meter below the ground surface as given in the problem statement. So this tells us the basic geometry of our problem. But we know that since our main objective is to find out the stresses, so in order to determine the stresses, we need to determine the unit weights. Without determining the unit weights, we cannot determine the stresses. So what kind of unit weights would we be using here? Now, since there are two different parts or two different kinds of stratum here, for example, above water table, the sand would be in dry state. Below water table, the sand would be in fully saturated state. So what kind of unit weights should we determine? Below the water table, we should be determining the saturated unit weight of the soil. And above the water table, if we consider the sand to be dry, we should be determining the dry unit weight of the soil. Now, how can we determine the saturated unit weight of the soil? We can determine the saturated unit weight of the soil by making use of the weight-volume relationships that we derived in our chapter number 1. So this is the simple relationship that can be used for determining the saturated unit weight of the soil. So by doing so, the saturated unit weight of the sand layer comes out to be 19.08 kilonewtons per cubic meter. In the same way, if we consider the soil here to be dry, we can determine its dry unit weight by using a similar expression that has been derived earlier by us. And by replacing all the values here, we can determine the dry unit weight to be 14.72 kilonewtons per cubic meter. Okay, so with the geometry done, let's move to part A of the problem statement. Now, the part A of the problem statement tells us, assuming the soil above the water table to be dry, so let's assume that this soil above the water table is dry, find out the effective stress at a depth of 6 meters below the ground surface. Now, how can we determine the stresses 6 meters below the ground surface? So, the first thing we can do is we can determine the total stresses acting over this soil stratum. How can we determine the total stresses? This is the total stress profile that can be developed. So what I've done is I've simply plotted a kind of a graph here. What I can do is I know at the ground surface, the stress would be 0. And then what I can do, I can determine the stress at this water, at the top of the water surface. At the top of the water surface, if I want to determine the stress, the total stress or the total load coming at the top of the water surface at 1 meter depth, what I need to do is I simply need to multiply the unit weight with the height of this layer. So simply by multiplying the unit weight with the height of this layer, I can determine the stress acting at 1 meter depth. Now, once I've determined the stress acting at 1 meter depth, if I want to determine the stress at 6 meter depth, what can I do? So first, remember, when I'm saying I want to determine the stress at 6 meter depth, what I want to know, what I want to see is that if there is a particle of soil here, or if there is an element of soil at this depth, what will be the total stress, or what will be the total load, or what will be the total pressure that is coming from the top, all the way from the top to this point. This is what we need to find out. Now, in order to find this out, what we can do is we can again do the same thing. We can we can multiply the unit weight times height of the first layer, which gives us 14.72, and then we can multiply unit weight times height of the second layer. The unit weight of the second layer is 19.48, and the thickness of this layer is 5 meters. That is from -1 meter to -6 meter, it is 5 meters. Now, by adding these two up, we get the total stress acting at this step. So this is the total stress, or the total weight, total stress caused by the weight of the soil which is above this point. So this is what we call as the total stress. But let's explore it a bit further, the same thing. Now, this is the total stress, but at this point, there would be some other stress acting as well. What would be that stress? Now, if you look closely, when I'm talking about 6 meter depth, this is the point which is below the water table. So this is the water table over here, and we are talking about this point. Now, when we are talking about this point, don't you think there will be some load acting because of the weight of the water over here as well? There will definitely be some stress because of the weight of the water over here. How can we determine this weight? The solution would be very simple. In order to simplify this statement that I've just made, let me give you a very simple example. If you have a tub of water, and let's suppose the height of the tub of water is 1 meters. So my question is, at the base of the tub, would there be any stress caused by the water that is present in the tub? Obviously, at the base of the tub, there would be stress caused by 1 meter height of water. So the same thing would be occurring here at this 6 meter depth. There would be some stress caused by this 5 meter height of water. And this is something that we can determine in terms of pore water pressure, which is represented by U. How can we determine the stress caused by water here? In order to determine the stress caused by water, we know that the stress caused by water would be zero at the top of the water level. The same as, for example, in case of a 1 meter high tub of water, at the surface of the tub, at the surface of water in the tub, the pressure because of water would be zero. But as we start moving down in the tub of water, the pressure because of the water would keep on increasing. The same thing would happen here. And so if we want to determine the pressure because of water at this depth, what we need to do is we need to multiply this height, which is 5 meters, with the unit weight of water, which is 9.81 kilonewtons per cubic meter. And by doing so, we can determine the stress because of water. And this stress, as we have seen in the previous classes as well, this pressure within the soil because of water is known as the pore water pressure, and it is represented by the letter U. So this is important for you to remember that the total stress is represented by sigma, and the pore water pressure is represented by letter U. Okay, so now we have determined the total stress, we have determined the pore water pressure. What now? Now let's assume that we have a 1 kilogram weight, the same kind of weight that we use to weigh different vegetables, etc., on a weighing scale. Let's assume that we have a 1 kilogram weight and we put that weight in a tub filled with water. Now, all of you know that the the weight of that object, which was exactly 1 kilograms, outside the water would become a little reduced. Why it would become reduced when it is inside water? Because of the uplift force or because of the bouncy force of water that is acting on it when it is immersed in water. In the same way, the stresses on the soil particles would be reduced when it is immersed in water. So the stresses at this depth, the stresses acting on the soil particles would not be equal to 110.12 kilopascals. Rather, the stresses at this depth, 6 meters, would be reduced in a certain way. And how can we determine this? The stresses at this depth on acting on the particles, on the soil particles, would be equal to 110.12 minus 49.05. In the same way as I'm immersing a 1 kilogram weight in a tub of water, and the weight would be reduced by the amount equal to the uplift force or the bouncy force of water. The same way the stresses acting on the soil particles would be reduced by the difference of these two. And these stresses are something we call as the effective stresses. Now, what do we mean by effective stresses is, we mean by effective stresses, which are represented by sigma dash, as the actual stresses acting on the soil particles. And how can we determine it? We can simply determine it by subtracting these two figures. So how can we do it? We can take again 2 points. So over here, it will be 14.72 minus 0 here, we'll get 14.72. So effective stress at this depth would be 14.72 kilopascals. And if I want to determine the effective stress at 6 meters depth, at this depth, it will be 110.12 minus 49.05. We'll get 61.07 kilopascals as the effective stress at this depth. Now, this is what was required by us, that we were required to determine the effective stress at a depth of 6 meters below the ground surface. We can determine it by using these figures, or we can in fact determine it simply by writing a formula for this. And how can we do it directly is something that you can try and understand by yourself. And if you cannot understand it, we'll discuss it more in the online discussion session that we are going to have. But let's explore a little bit more that what is the physical meaning of these effective stresses. Now, this equation here is a very important equation in soil mechanics. And what this equation tells us that the effective stresses, sigma dash, equals the total stresses minus the pore water pressure. It means that if I want to determine the effective stresses acting on the soil particles, what we have to do is we have to subtract the pore water pressure from the total stresses. What is the physical meaning of this? In order to understand the physical meaning of this, let's have a look at this figure. Now, what we have in this figure is, you all know that soil is a three-phase medium. And in that three-phase medium, we have the solid particles, and we have air, and we have water. Let's assume that we have a fully saturated soil as shown here, in which all the voids are filled with water. Now, on this fully saturated soil specimen, we apply a certain load on it. When we apply certain load on it, the applied load would be represented by the total stress. That is the total load that we have applied on the soil particle. This is what we mean by the total stress given here. That is the total load that is applied on the soil particle at this step. So 110.12 is the total load that is applied at this step. Now what happens is that when you apply certain load on the soil specimen, because the voids within the soil are very, very small, because of the application of this load, water, the soil starts getting compressed. And when the soil starts getting compressed, the water tries to escape through these voids. But because the voids are so small, water cannot easily escape through the voids. And if the water cannot escape through the voids easily, obviously the pressure of water keeps on increasing. So the pore water pressure, which is U, it will keep on increasing. And what it will do is it will try to push the particles away from each other. So when you apply the total stress, when you apply the total stress, the pore water pressure, the water pressure within the pores, it will increase, and this increased pore water pressure will try to push the particles away from each other. Now, once this will try to push the particles away from each other, the particle to particle contact force, it will start on decreasing. So you see the particles which are in contact with each other, this interparticular contact will start on decreasing because the water pressure within the pores is actually pushing the particles away from each other. So this is why the effective stress, which is the particle to particle contact, it keeps on decreasing. So what we mean by the effective stress is the effective stress, which is represented by sigma dash. The basic definition of this effective stress is that it is the particle to particle contact stress within the soil. So total stress means the externally applied load, the load that we are applying externally. And the effective stress means the stress which is actually being transferred from one particle to the other particle, from this particle to the other particle, and so on and so forth. In order to understand this example in a little better way, you can also think of a dishwashing sponge like this. Now let's assume that you have a certain sponge like this, and in this sponge, let's assume that on this dry sponge, you put certain weight on top of it. Once you put certain weight on top of this dry sponge, all the weight that you put here, all the weight is being carried by the particle to particle contact force. However, there is another thing that you can try. If you make it wet, if you submerge it in water, you make it wet, and then you put some weight on top of it, the water will try escaping through the voids. The water will drain out of these voids. But you know there are certain sponges available in the market in which the particle size, the void size is very, very small. Now, if the void size is very, very small, when you put weight on it, water cannot escape out of it. When the water cannot escape out of it, the weight that you have put externally, some of this weight is going to be taken by the water which is within the voids, and the rest of the weight is something that is going to be taken by the interparticle forces. So this way, from this, if you can imagine this load transfer mechanism as I've tried to explain here, you can imagine the difference between the total stress, which is the external load, pore water pressure, which is the pressure exerted by the pores within the soil skeleton, and the effective stress, which is the interparticular contact. So this is some basic definition of the total stress, pore water pressure, and effective stresses. Now with this, let's move to part B of the problem. Now part B of the problem statement says, if the soil above the water table is saturated by capillary action, sketch the total stress, pore water pressure, and the effective stress diagrams for the sand deposits for a depth of 6 meters below the ground surface. Now, there's one little difference in this problem which we'll explore on our way of solving this. So first of all, we have to draw the total stress diagram. Now, how can we draw the total stress diagram? Before going on and drawing the total stress diagram, we have to first consider this thing. In the previous part of the problem shown here, it was told us that the top portion of this top portion of the top 1 meter of the soil is dry. Soil above the water table is considered dry. But in part B, it has told us that this top portion, the top 1 meter, is also saturated because of the capillary action. So if this top 1 meter is also saturated, so it means in the top 1 meter, we should consider gamma saturated and not gamma dry. So by knowing this, what we can do is we can draw the total stress diagram in a similar way. We can determine the total stress at 1 meter depth as the unit weight times the depth of this layer, which will come out to be 19.08 kilopascals. And in order to determine the total stress at this depth, what we can do is we can unit weight of the whole soil is obviously the same. All is 19.08 multiplied by 6. So this is how we can determine the total stress at this depth. Now, how can we determine the pore water pressure? Now, determination of pore water pressure is a little interesting here, and this will be slightly different compared to what we have done previously. So this is how the pore water pressure profile would look like. Important for you to know is that although the problem statement says that this zone above the water table is saturated, but it tells us that this zone is saturated because of the capillary rise of water. Now, what is capillary rise? Capillary rise means that above the water table, there is certain depth above the water table, the soil gets saturated. Why it gets saturated? Even if the water table is up to this depth, so because of the small little pores within the soil, the water is sucked upwards. Because of the suction, the water is sucked upwards, and some zone above the water table also gets saturated. So the actual water table, although may be at -1 meter, but some part of soil above the groundwater table also gets saturated. So how can we draw the pore water pressure diagram? Let's first of all look how to draw the pore water pressure diagram beneath the water table. Beneath the water table, it will be positive pressure, and positive pressure would be like the unit weight of water multiplied by this height. So 9.81 multiplied by 5 would give us the positive pore water pressure. And because above the water table is negative pore water pressure, because this soil is saturated, but it is saturated because of suction, and suction is always the negative pore water pressure. So you need to just remember this thing for the time being, that suction means negative pore water pressure. So capillary rise is caused by suction, and if you want to determine this negative pore water pressure, it would be the unit weight of water multiplied by the height of this layer, which would give us this -9.81, and we'll be here. And then finally, in order to determine the effective stresses, to draw the effective stress diagram, it should be very simple. And if you remember, what we did was the effective stress diagram would simply be the difference of these two figures. So whatever is the value here minus this one, we will get the effective stress at this point. In the same way, we can determine the effective stress at the second point of interest, which will be again 19.08 minus 0 will get 19.08 kilopascals. And finally, in the similar way, we can determine the effective stress at this step, which will be 114 minus 49 will get the effective stress at this step. So in this way, we can draw the total stress, the pore water pressure, and the effective stress profile of our problem. Let's solve another problem. So we are required to determine the total stress, the pore water pressure, and the effective stress of the soil stratum at 6 meters and at 16-meter depth from NSL. So the problem is a little different one this time. For example, this is the natural surface level, and you see the water table is above 12 meters above the water, above the natural surface level. So what you can get from this is you can probably assume that this is the bottom of an ocean where the water level is higher than the ground level. And beneath the ground level, there are two stratum we have stratum A, which has saturated unit weight given here, and we have a stratum B with the saturated unit weight given here. So what we are required to do is we are required to determine the effective stresses at 6-meter depth, which is here, and at 16-meter depth, which would be somewhere over here. So let's see how can we determine the effective stress at these 2 points. So I've redrawn the same figure myself. So this is NSL water table 12 meters above the natural surface level. We have stratum A with the unit weight, the saturated unit weight given. We have stratum B with the saturated unit weight given. 16 meter is the depth where we want to find out the effective stresses. So how can we determine the effective stresses? Again, the first step should be to plot the total stress profile. And how can we plot the total stress profile? Plotting the total stress profile means whatever is the unit weight of a particular layer, multiply it with the height. Since this is a water layer, so the unit weight of water is 1000 kilograms per cubic meter times the height of this layer, we get 12,000 kg per square meter. And then once I want to determine the stress at 6 meters depth, the stress at 6 meters depth would be the stress acting at this point plus the stress because of this stratum A. So stress at this point was 12,000 plus stress because of this second layer, which would be the unit weight of this layer, 1856.7 times the height of this layer, we get 23,136 kg per square meter. In the same way, we can determine the stress at 16 meters depth and also at 20 meters depth. So if I want to determine the stress at 16 meter depth, it would be the stress up to this point, which is 23,136 plus unit weight of this layer into height. So 23,136 plus the unit weight 1952.8 multiplied by the height, which from 6 meters to 16 meters would be 10 meters, we'll get 42,664. And in the same way, we can determine the total stress at 20 meters. Now, the second step, if you remember, would be to determine the pore water pressure. So the pore water pressure profile can again be determined in the same way. At the surface of the water table, it will be zero pressure. And as we go along in depth, we can determine the pore water pressure simply by multiplying the height of the layer with the unit weight of water. So the unit weight of water is 1000 kg per cubic meter. 1000 multiplied by 12,000, we would get 1000 multiplied by 12 meters layer, we would get 12,000. In the same way, we can get 1000 multiplied by depth up till here, which is 18 meters. So this is 6 meters up till here and 12 meters up till here. So 12 plus 6 is 18. We'll get 18,000. Or other way, we can do it in the same way as we have done for the total stress. So in order to get 18,000, so the stress at this point would be equal to the stress at this point, which is 12,000, plus the unit weight of this layer multiplied by the height of this layer. So 12,000 plus the unit weight of water in this zone would be 1,000 multiplied by 6, So 12,000 plus 1,000 multiplied by 6 would give us 18,000. And in the same way, we can determine the pore water pressure of the rest of the layers. And finally, to determine the effective stresses, all we have to do is to subtract the total stress from the pore water pressure to get the effective stresses. So we subtract the ordinate of total stress at plus 12 meters depth. From this one, we'll get 0. Same would be the case over here. And when we come to this depth, it would be 23,136 minus 18,000. We get the stress at this level. And by repeating the same procedure, we can determine the effective stress at the rest of the points. So this is all how we can solve this problem. Then there is another problem given here, but this problem we will not solve here. I would in fact give you the answers of this problem, and I would request you guys to try solving it by yourself using the same procedure that we have adopted for the previous problems. And if you have any problem, then we can discuss it during the online discussion session this week. And let's solve one more example here. In this example, let's go through the problem statement. A layer of sand extends from the ground level to a depth of 9 meters and overlies a 6 meter thick layer of clay having very low permeability. The water table is 6 meters below the surface of sand. The saturated unit weight of the sand layer and the clay layer is given to us. The unit weight of the sand above the water table is given here. So what do we have here is we have a sand layer, and below the sand layer there is a clay layer, and the water table is given at a depth of 6 meters below the ground surface. So what it says is over a short period of time the water table rises by 3 meters and is expected to remain permanently at this new level. Determine the effective stress at a depth of 18 meters and 12 meters below the ground depth. Now, in order to understand the problem statement, the first step that we should do is we should sketch this problem, because with me, reading the problem, it's always going to be very difficult for anyone to comprehend it. So let's draw a sketch of this figure, which I have drawn here for you. So we have a sand layer which is 9 meters thick, and this overlies a clay layer, which is given here. And important for you to remember is that it was given in the problem statement that this clay layer has a very low permeability. So then it says that the water table, which is given here, after some time, this water table was raised by 3 meters. So this was the new water table. So that's why I'm calling it water table number 1, and I'm calling it as the water table number 2. So what is required by us? We are required to determine the effective stress. Now, I hope you would remember that sigma dash represents the effective stress. So we are required to determine the effective stress at 8 meters and at 12 meters depth. So we are required to determine the effective stress at 8 meters and at 12 meters depth. But in 2 cases, we need to determine the effective stress immediately after the water rise and long time after the water rise. So how can we determine the effective stress at 8 meters and 12 meters depth in these 2 conditions? Once the water level was raised, so initially and after a long period of time. So in order to solve this, let's first of all look at part B of the problem statement. Let's first try to solve part B, and then we will solve part A. So if I want to determine the effective stress at 8 meters depth, how can we determine the effective stress at 8 meters depth? Now, you know, in order to determine the effective stress, all I have to do is I have to determine the total stress at point 8, at this point, and then I have to determine the pore water pressure at this depth. So first I'll determine the total stress, then I'll determine the pore water pressure. I will simply subtract these 2 and I will get the effective stress. This is what I'm going to do over here. So for 8 meters depth, This is how we can determine the total stress at 8 meters depth. Now, in order to determine the total stress at 8 meters depth, now the water level has, remember the water level has been increased to this level. So in order to determine the total stress at 8 meters depth, what I need to do is I need to use the bulk unit weight times the height of this layer. This is 16 multiplied by 3 plus the unit weight of this layer times the height. So this part is below the water table. Once this is below the water table, it means I have to use gamma saturated here. Now, when I'm using gamma saturated, so gamma saturated is 19, and how much should be the height? From this point to my required point at 8 meters depth, this is 5 meters. So minus 3 and 8, it becomes 5 meters. So by doing this, we can determine the stress at 8 meters as 143 kilopascal. Then to determine the pore water pressure, how can we determine the pore water pressure? The pore water pressure at this depth would again simply be the unit weight of water multiplied by the depth of water. So we know the unit weight of water in kilonewtons per cubic meter would be 9.81 kilonewtons per cubic meter, and the depth of water would be 5 meters in this zone. So this is how we can determine the pore water pressure at this depth. Then finally, if we want to determine the effective stress, we know effective stress is simply the difference between the total stress and the pore water pressure. So how can we determine the effective stress? We simply have to take the difference of these two. And by taking the difference of these two, we can determine the effective stress as 93.95 kilopascals. In the same way, we can determine the total stress and the effective stress at 12 meters depth. Now, how can we determine the effective stress at 12 meters depth? First, let's determine the total stress at 12 meters depth. Now, we can adopt the same philosophy that we have used for the determination of total stress at 12 meters depth as we have used here. We simply have to multiply the unit weight of each of the layers present above this depth with the corresponding depth of that layer. So let's see how to do it. So it is 16 multiplied by 3 means the unit weight of this layer times the height of this layer plus 19 times 6. 19 is the unit weight of this layer times the height of this complete layer, then plus the 20 times 3, 20 which is the unit weight of this layer plus 3 which is the height of this layer from 9 meters to 12 meters. So simply by doing so, we can determine the total stress at this depth. Now, how to determine the pore water pressure? For the determination of pore water pressure, once again, all we need to do is we have to multiply the unit weight of water with the corresponding height of water above 12 meters. So height of water above 12 meters is 3, 12 minus 3 would be 9 meters. So 9.81 times 9, we get the unit weight of water. We get the pore water pressure of water, in fact. And then finally, for the determination of effective stress at this point, all we need to do is to subtract the total stress and the pore water pressure, and we get the effective stress at this step. So this will be the effective stress at this step long time after the water rise. Now let's see how to solve part A. What will be the difference? What do you guys would feel would be the difference in the water level immediately after the water rise? So let's see how, first of all, how to determine the effective stress at 8 meters depth. Now, for the determination of of effective stress at 8 meter depth would not be any different as you have done previously. So for the determination of total stress, all we need to do is multiply the corresponding unit weights with the corresponding heights, and we get the total stress. Then we can determine the pore water pressure and the effective stress in exactly the same way as we have done before. But what about this 12 meters depth? Now, what is the difference, basic difference between 8 meters and 12 meters depth? The basic difference between 8 meters and 12 meters depth is that this 8 meters point is present within the sand layer. And we know that sand is a porous medium, and the pore water pressure can easily build within sand, and it can easily dissipate within the sand layer. And whereas in case of clay, the soil is impermeable, or the soil is has very low permeability, and because of this, the pore water pressure can build up inside. So that is the basic difference. So the question is, what would be the effective stress immediately after the water was raised from this level to this level? So let's first of all determine the total stress at this depth. Now, once we want to determine the total stress at this depth, the total stress would not be any different as you have computed earlier. So the total stress can be computed exactly the same way as you have calculated earlier. However, if once we want to try to determine the pore water pressure at this depth, the calculation of pore water pressure would be slightly different compared to what you have done over here. Previously, when we were considering the case of long time after water rise, we calculated the pore water pressure as the unit weight of water times the height of water above this point. And the height of water above this point was 9 meters. How did we get this 9 meters? It was 12 minus this 3 meters. So the this was the pore water pressure long time after the water rise. However, if we consider the short-term case in which we consider the pore water pressure immediately after the water rise, it will be slightly different. And what will happen is immediately after the water rise, so once the water level was increased from here to here, so although the water level has been increased, but because of the very low permeability of this clay layer would not realize that the water level has increased. This clay layer would need considerable amount of time in which the pore water pressure within this clay layer would increase because of the increase in this water layer. And after that considerable amount of time, only after a considerable amount of time, this increase in water level will be reported by this clay layer. Because of this reason, while determining the pore water pressure at this point, immediately after the water rise, we can simply determine it by multiplying the unit weight of water with the height of water from the previous water level. So in this case, immediately after the water rise, we will be using the old water level for the determination of pore water pressure. And it will be this 12 meters minus 6 meters, so it will be 6 meters here. And finally, the determination of effective stress is very simple. It is simply the difference between the total stress and the pore water pressure. So I hope with this example, you might be a little clear about how to determine pore water pressure under or the effective stresses under different scenarios. And another thing that we have tried doing here in this example is that we have tried to determine the effective stresses, without the earth pressure diagrams that we have drawn in the previous example. Now, there are certain further example problems that you can try to consolidate your concepts. So I have the PDFs of all these books are easily available over the internet. So I would suggest you guys to go through these problems, these solved examples, most of them, to further consolidate your concepts. That's it for the day. Thank you very much.